Hello everyone, I'm Shivanya Gonde and I'm a PhD student at Ulish Washing Center MIK2, and today I will be going to present my research on thermochemical modeling of oxide systems relevant for solid state batteries. So we are all aware that the conventional sources of energies which are non-renewable in nature are getting exhausted. So there is a constant shift to extract energies from renewable sources such as sun, water, biomass and wind. The energies obtained from these sources are clean and green but highly fluctuating in nature. It is therefore crucial to store these energies for practical applications such as illumination or transportation. One such example of an automotive cell is called the zebra cell. In zebra cell, beta double prime alumina serves as the ceramic electrolyte. The processing of this electrolyte is highly elaborate, sophisticated, and requires high processing temperatures of about 1600 degrees. Moreover, this material has a layered structure and sodium ions migrate between two-dimensional conducting planes only. To overcome this restriction, 2019 Nobel laureate in chemistry Sir Goodenough has proposed a three-dimensional structure with this composition, and this material, besides having similar ionic conductivity, has a three-dimensional structure in which sodium ion migration takes place in three-dimensional voids. This composition is part of the quaternary oxide system, and this can be represented by a tetrahedron. So, in the vertices of the tetrahedron represent unary system, the edges represent the binaries, the faces represent the ternary system, and the region of space that this tetrahedron encloses represents a quaternary system. In this quaternary system, there is an interesting phase called the NASICON phase, which is shown here, which is found to be conducting in nature, and therefore it can be applied to battery materials as electrode and electrolyte material. The other advantages that this material provides is that because of large sodium abundance and lower manufacturing cost, we can produce cheaper batteries, and because of low toxicity, it is safe to produce and use. For the application of this material as a battery material, not only conducting properties but also thermodynamic properties such as stability of the phases and their phase behavior should be known before. In order to predict that, we need thermodynamic calculations. For calculation, we need database, but because database is not available, we are generating database based on CalFed method and also using experimental data. I would like to mention that this database creation is a joint cooperation between IEK2 Forschung Centrum Jülich and GTT-Technologies, and my contribution will be a part of a big database called GT-OX in the future. So in this quaternary system, the thermodynamic datasets of three binary and one ternary systems have been studied before, and today I would like to discuss the remaining binary and one ternary system that I have uh, performed in my PhD work. So in this zirconia phosphor system, there is an experimental phase diagram available, um, and with the following invariant points. This has been utilized for modeling, and also thermodynamic data for 3:2 and 1:1 compound have been considered. For the modeling, we not only need to know information about solid compounds but also about liquid. And in the case of our modeling, we have utilized modified associate species model in order to be compatible with the other systems present in the big database. After successful modeling, we have compared our results with the experimentally available information, and in this manner, we have created thermodynamic datasets for the systems. In this system, we have four solid compounds, and in the absence of any heat capacity data, we have used Neumann-Kopp approximation, which is the stoichiometric sum of the oxides, and the enthalpy and entropy data have been optimized, sometimes based on experimental value when it was available. For the modeling of the liquid phase, we have considered the slag constituents, so zirconia and pito 5, and also the associate species. And for the modeling, we have considered the interaction between the N members and the associate. After successful modeling, we have been able to uh, create thermodynamic data sets. And as you can see that the values are very precise as compared to that of the experimental data. So precise data set for this system has been created. Moving on to the next binary system, zirconia silica system. So this system has been studied extensively in the past, and here is the summarized picture of all the experimental data available for this system. So there are two important things in the system. So because of the presence of silica, we expect a miscibility gap in this region, and there is a eutectic point near silica end. Um, Also, there is 1:1 compound with temperatures from 1500 to 1800 degrees. So the eutectic temperatures and the decomposition temperatures are comparable, but in most studies, the eutectic temperatures are greater than the decomposition temperature. So thermodynamic data for zirconia silicate has been uh, there from before based on the experimental data, and also heat capacity information has been derived from it. In our study, we have adopted heat capacity equation from Coughlin and King for the modeling of this compound. Moreover, we have adopted enthalpy of formation value based on high temperature solution calorimetric study from Ellison. For the modeling of liquid, we have considered strong interactions between zirconia and silica, and we have been able to model the miscibility gap precisely. As and in our study, we have also obtained the eutectic temperature and decomposition temperature. They are comparable in values, but and as per the consensus of most of the studies, also our eutectic temperature is greater than the decomposition temperature. When we compared our results to that of the previously assessed data set for this system, we can see that we have been able to describe miscibility gap with sharp endpoints and also based on the experimental data. Moreover, we have improved liquidus uh, in 0 to zero point 0.4 mole fraction of silica region, and it agrees very well with that of Zirnova's and Telle's experimental points. Furthermore, we have good representation of the liquidus from zero point 0.8 to 1 mole fraction of silica region, and they are very close to that of the experimental points. In this manner, we have created a good data set for zirconia silica system. After having the three binary systems model, now it's time for the ternary system. And this system finds application as proton conducting glasses, and there is only one literature about the system, and it mentions subsolidus equilibria based on the experiments, and there is no ternary compound in this system, and we wanted to create thermodynamic data set for this system. So in this ternary system, here is the schematic representation of all the binary of the compounds present in the binary systems, and we have thermodynamic data sets of silica phosphor, zirconia phosphor, and zirconia silica. In the absence of any ternary compound, only the interactions in the liquid phase were modeled, and in this manner we have obtained a preliminary data set. This preliminary dataset was utilized for the modeling of the subsolidus equilibria, and when we compared our model with that of the experimentally obtained subsolidus equilibria, we see that they are in good agreement. Moreover, uh, uh, we have 1:2 compound which has been found after this study incorporated in our database, and because of the consideration of different references for 2:1 and 3:2 compound, theirs being with the solid solution one and ours without, so we have this as a difference. Based on the preliminary data set, we have also predicted the liquidus surface, and this can be directly applied to the battery materials development. And in order to validate the predicted uh, liquidus surface, we have performed some experiments using different compositions of materials and studying them using XRD and DTA. And we are in the process of incorporating them into the database. Moving on to sodium containing systems. So, sodium zirconia system. Recently, a study has been published, and this system has been assessed based on modified quasi-chemical model for the liquid phase, and also there were experiments in this system for on which this phase diagram is based. So their own experiments and also experiments from the previous studies. But in our case, we want to use modified associate species model for compatibility. And in this system, there is sodium zirconate present, and the compound stability can be summarized in this picture. And there is not so much melting information available for this compound. And we have adopted the experimental points of specific heat capacity from the study of Bayer and created our CP equation for the same. And this will be utilized for the modeling of sodium zirconate. And on the experimental side, we wanted to investigate the real thermal behavior of this compound, so transition and melting, and also the formation enthalpy. And for this investigation, we have utilized a very specialized method called Knudsen effusion mass spectrometry. And in this method, equilibrium is considered between the condensed phase and the gas phase. So here is a general scheme. So this is the Knudsen cell, and the size of the orifice is very small as compared to the size of the lid. So there is always an equilibrium maintained between the condensed phase and the gas phase, and only very few molecules can escape. So this maintains near equilibrium condition, and at different temperatures, the gaseous species can be ionized, and this can be studied using mass spectrometry. In this manner, we can study vapor pressure and other thermodynamic properties. And in our study, we have measured the intensity of the ion, and we have calculated the partial pressure of the gaseous species from the intensity. So using this equation, so this is the calibration constant in this temperature range, and intensity, temperature, and the cross section area of the species. And this can lead to formation enthalpy of sodium zirconate. And using this plot, so here so these are the experimental points for sodium, and the red line indicates uh, the formation enthalpy from our study, and this is 50 kilojoule different from Bayer's value. And this formation enthalpy will be utilized for the modeling of the sodium zirconate solid compound. For the modeling of the liquid phase, we have considered interactions between the associate and the end members. And for the modeling of the solid solution, we have adopted one lattice, one polynomial model from Lee's study. And this can be seen here. So we are able to successfully model this area. So these are the experimental points from this study, and we are able to successfully model that. Currently we are incorporating melting point values for this thermodynamic data set. So to summarize my presentation, we have successfully achieved thermodynamic data sets of zirconia phosphor system, zirconia silica system, zirconia silica phosphor ternary system, and sodium zirconia system. And in the future, thermodynamic data sets of the remaining ternaries and the quaternary system will be created based on these data sets. This is our contribution for a sustainable development of battery materials to provide a greener future. I would like to thank my supervisors, Elena, Dimitri, and Michael, for their excellent guidance, and my other colleagues for their experimental support. in IK2 for the excellent research infrastructure and high-tech fellowship from the Helmholtz Society for supporting me during my PhD. Thank you very much, and I look forward to your questions.